Hello! Thanks for watching, and welcome to the next video in my series on basic statistics. Now, as usual, a few things before we get started. Number one, if you're watching this video because you are struggling in a class right now, I want you to stay positive and keep your head up. If you're watching this, it means you've accomplished quite a bit already. You're very smart and talented, but you may have just hit a temporary rough patch. Now, I know with the right amount of hard work, practice, and patience, you can work through it. I have faith in you. Many other people around you have faith in you. So should you. Number two, please feel free to follow me here on YouTube, on Twitter, on Google+, or on LinkedIn. That way, when I upload a new video, you know about it. And it's always nice to connect with my viewers online. I feel that life is much too short and the world is much too large for us to miss the chance to connect when we can. Number three, if you like the video, please give it a thumbs up. Share it with classmates or colleagues or put it on a playlist. That does encourage me to keep making them for you. On the flip side, if you think there's something I can do better, please leave a constructive comment below the video, and I will take those ideas into account when I make new ones. And finally, just keep in mind that these videos are meant for individuals who are relatively new to stats. So I'm just going over basic concepts, and I will be doing so in a slow, deliberate manner. Not only do I want you to know what is going on, but also why and how to apply it. So, all that being said, let's go ahead and get started. Now, in our last set of videos, we learned how to form confidence intervals and conduct hypothesis tests for single population data. For example, let's say a manufacturer claims that a container contains 64 ounces of orange juice. We could take a single sample of bottles and then construct a confidence interval for the mean number of ounces and conduct a hypothesis test where the null hypothesis states the mean equals 64 ounces. We don't expect the mean to be exactly 64 ounces, but very, very close. In a two-population scenario, we compare not one, but two population means against each other. So in our orange juice example, we could test the bottles in two different factories to see if the mean number of ounces in each bottle is the same or different across the two factories. Note, we're not comparing the means against an assumed value. We're comparing them against each other. So the means could be equal at 60 ounces, but that would be a very bad thing given the label claims 64. Now, many students I've worked with learn two sample tests in class without actually knowing what they are or why they even exist. So this video offers a solid conceptual foundation about two sample tests, comparing the means using illustrations and graphics. So, if you are new to these techniques or are still trying to figure out exactly what they are, this video is for you. So, sit back, relax, and let's go ahead and get to work. Now, to fully understand the topic of this video, you will need to have had experience with or knowledge of the following concepts. What point estimators are, like the sample mean. Sampling distributions. What the standard error is. What the margin of error is. What confidence intervals are. And how to find t-values for a given alpha level and sample size / degrees of freedom. So this video is an extension of these topics in the context of analyzing the difference between two populations. So if you think you have all these down, we'll go ahead and dive right in. When we're looking to differentiate or compare two distributions, there are two primary characteristics we can analyze. We can analyze the location of their means relative to each other. So the means could be located in different places, or the means could be right on top of each other. We could also compare their variances, or the spread of the distributions. So if one distribution has a large standard deviation, it would be a wider distribution. If one has a smaller standard deviation on the same units, it will have a more narrow distribution. So we could look at the location of the means, or their variances, or their spread. So we can look at the location of their means. So the distributions could have the same variance like they do in this image, but the means could be very, very far apart, or they could overlap quite a bit. Now we could also look at their variances and notice that the location of the means of these two distributions do not move. The only thing that's moving here are the distributions. So if the means are relatively close like this, but the distributions are narrow, we can separate those distributions quite a bit. But if the distributions are very wide, then the curves overlap and the distributions become hard to separate, even though the means are in the same place. So always keep this in mind. We're looking at the location of the means and the spread or the variance of each distribution at the same time. So a few things before we get started. When the population standard deviations, or sigmas, are unknown, we must estimate them using the sample standard deviation, S. Now, since S is by definition an estimate, it will not be perfect. Therefore, we switch from using the standard normal distribution, or the Z distribution, to utilizing the T distribution with a certain degrees of freedom. In this case, degrees of freedom are computed using an ugly formula we'll learn a little bit later. Actually, it's not that bad. There are other ways to compute the degrees of freedom. However, we are going to learn the one that requires the fewest assumptions and is universally applicable. So let's start with a problem like I always like to do in my videos. So let's say you're the manager of 2 call centers in Bangalore, India. These centers focus on in-depth problem solving for clients. Therefore, the calls last approximately 12 minutes. Each location has its own employees, its own management, and its own work culture, so they are independent of each other. As part of your performance analysis, you wish to see if there is a difference in the average call length between both locations. The assumption is that the mean difference between the 2 locations is 0. That is, there is no difference in the mean call length between the 2 call centers. So a random sample of 30 calls will be taken from both call centers to conduct our test. So call center 1 is over here on the left, and call center 2 is over here on the right. Now, we did our analysis, and we have 2 means and 2 standard deviations. So mu sub 1 is the mean for call center 1, and then S sub 1 is its standard deviation of 1.2 minutes. Mu sub 2 is the mean for call center 2 over here on the right. Now the S sub 2 is its standard deviation of 1.5 minutes. So what is our assumption here? We're assuming that the mean difference is 0, that the difference between mu1 and mu2 is 0. Or we can say it another way. We're assuming that mu1 and mu2 are the same. That's kind of 2 ways of saying the exact same thing, but technically we write it mu1 minus mu2 equals 0. Now what about independence? These 2 call centers are independent of each other. And that's very important when you're doing an independent samples t-test. We will do a matched sample later on in this playlist, but for now we are assuming that both samples are independent of each other. So what about the distribution of the difference between these 2 means? So again, mu1 is the mean call length for call center 1. Mu sub 2 is the mean call length for call center 2. So what are we actually doing here? We take an independent sample from call center 1, which is mu1, that'll be its mean. Now since it's a sample, it will be x bar sub 1, because remember, x bar is the sample mean. Mu sub 1 is the population mean. But since we're taking a sample, we will call it x bar sub 1. So we'll take a sample of 30, and that'll be x bar sub 1. Then we'll take an independent sample from the second call center. That will be x bar sub 2. So that would be a mean of 30 calls. Then we find the difference between those 2 means. So x bar sub 1 minus x bar sub 2, and that will give us d sub 1, or the difference between those 2 sample means. And then theoretically, we return to step 1 and repeat the process. And what happens is we get a distribution of the differences. So by taking a sample of each, finding the difference, we get the one difference, then we'll do it again, we'll get another difference, do it again, get another difference, and in the end, we will have a sample of differences. So x bar sub 1 minus x bar sub 2, or d for the difference, is a point estimator of the difference between the two populations. So the difference in the sample means, d, is a point estimator of the population mean differences. So let's say we did that, and we did it 10 times here. So the first time we took a sample of 30 from call center 1, we had a mean call length of 11.91 of those 30 calls. Then we did the same thing for call center 2, and that has a mean of 12.02 minutes. So the difference between those two is minus 0.11 or negative 0.11 minutes. Then we do it again. We take 30 from call center 1, we get a mean of 11.36. Then we get the same sample from call center 2. By chance, we get a mean of 12.02 again. The difference between those two sample means is negative 0.66 minutes. And then we do it again. So in theory, we do this over and over again, and we get a distribution of many differences. So each d sub I just means iteration, by the way, it means the next, is a point estimate of the difference between the two population means, mu sub 1 and mu sub 2. The d sub I values form a distribution of differences. In the same way, single sample means have their own sampling distribution. So it's a sampling distribution, in this case, of differences, of independent samples. Now we can take the mean of those differences and we get d bar. And d bar is the mean of the differences. So the standard error of the differences, if we don't know sigma, the population standard deviation. So let's compare this to what we already know in the single sample case. So the standard error of the mean in a single sample is s divided by the square root of n. So s is the standard deviation divided by the square root of n, which is the sample size. And that gives us the standard error of the mean. And remember, the standard error of the mean is the standard deviation of the sampling distribution. Now, what about in this two independent random sample case? Well, if you notice, it looks pretty similar. So instead of s sub x bar, like we do on the left, on the right, we have s sub x bar sub 1 minus x bar sub 2. So that is the standard error of the difference. And that equals the square root of the standard deviation squared sub 1 divided by n sub 1. You can go ahead and read that. I'm not going to read all that under the radical sign there. But if you notice, it looks very similar to what we have over here on the left. So on the left, we have the standard error of the mean for a single sample. And then over here on the right, we have the standard error of the difference when we're looking at two independent random samples. Now we can rewrite that as s sub d bar equals the same thing. Because remember, on the right here, the subscript with the s, it means the same thing. So what about the interval estimate for a single mean as it compares to the interval estimate of the difference for two independent random samples? So remember, in the single sample, we had x bar, our sample mean, plus or minus some margin of error. Now over here in the two independent random sample cases, we have the same thing. But now we have d bar, which remember is the mean of the differences, plus or minus some margin of error. Very similar. Now in the single sample case, the margin of error when we're doing sample statistics is t, remember we're using the t distribution because we're using a sample, sub alpha divided by 2. So in this case, it's a two-tailed case. So if our alpha was 0.05, the t we're looking at would be t 0.025 because we're looking at it on both ends. And then again, that's multiplied by the standard error, which is there in the red, s divided by the square root of n. So the margin of error is just the standard error, there in the red, multiplied by the area of the t distribution we are interested in. Now over here on the right, for the difference, again, very similar. So we have t sub alpha over 2 Again, that's just our alpha level divided by 2 because we're looking at two tails in the distribution. And then again, the red is our standard error, just like we saw it on the last slide. So if we put it all together, the interval estimate for the single sample mean was x bar plus or minus t sub alpha over 2 times the standard error, s over the square root of n. That should look familiar from the single sample videos or your single sample work in class. Over here on the right, exact same formula, or exact same structure of the formula. D bar, which is the mean of the differences, plus or minus t sub alpha over 2, again because we're using a two-tailed distribution for the differences, times the standard error, which is there in the red. So I just want to show you that the differences in terms of the formulas and how they're actually constructed in terms of their intervals, it's the exact same thing you saw, pretty much, or the same structure at least, as when you were doing the single mean interval estimate. Same basic idea. Now what about this degrees of freedom calculation? Now, finding the degrees of freedom when using the t-distribution with two independent random samples uses a more involved formula. As you can see here, there are a lot of elements that go into this degrees of freedom. Now, the good thing is it requires 4 pieces of information you already have. So, S sub 1 is the standard deviation of sample 1, S sub 2 is the standard deviation of sample 2, N sub 1 is the sample size of sample 1, and N sub 2 is the sample size of sample 2. Now, the thing to keep in mind here is that this does not require the samples to be the same size. It accommodates samples of different sizes and things like that, so that's what makes it more flexible. This is also the version that makes the least number of assumptions about your two distributions. So therefore, we use this one in almost every case. Let's go ahead and find our degrees of freedom for the call center problem we are using. So S sub 1 was 1.2 minutes, that's our first sample standard deviation, and our N was 30. And then for call center 2, we had a standard deviation of 1.5 minutes, also with a sample size of 30. So all we have to do is insert that into our degrees of freedom formula over here on the right, do a little bit of math, and we come up with the degrees of freedom of 28.873. Now when we do this type of test and we get a decimal as far as our degrees of freedom, we always round down. A lower degrees of freedom will create a more conservative interval in our t-distribution. So just remember, always round down. So what about the interval estimate for call length? Now we have everything in order. So here is our information. So we have call center 1 sample size of 30, our standard deviation of 1.2, actually I should say S over there with the given, 1.2. Then call center 2 is 1.5. So those are our standard deviations. Degrees of freedom were 28, which we just figured out. Our alpha level we're going to choose, which is pretty standard, is 0.05. And the t critical is plus or minus 2.048. Now, where does that come from? Well, remember, it comes from our t table with an alpha of 0.05 and degrees of freedom of 28. So that will be the critical value on either side of our distribution in the tails. So again, I assume you know how to read a t table at this point. Now over on the right, we have our formula for the interval, d bar plus or minus t sub alpha over 2 times the standard error there in the red. So that's everything we've already covered. No big surprises so far. So all we do now is we substitute our numbers into the interval estimate formula. So we substitute our t critical in there where the t alpha sub 2 is. They're in the purple color. And then our standard errors, they're in the red. Go ahead and continue our math out. And we come up with an interval estimate for the difference in the call length is d bar plus or minus 0.7183. The 0.7183 is our margin of error. And as long as the samples are the same size, that will be the margin of error for every 30 sample we take from both call centers. So as long as everything else remains the same, if we take another sample of 30, another sample of 30, this margin of error will remain the same. And we also have to assume, of course, that the standard deviations would remain the same. So if the S's and the n's remain the same, then this margin of error will also be the same. Not likely, but it could be. And then d bar will be whatever the difference is when we find our sample difference. So this is the 95% confidence interval for the estimate of the mean difference, d bar. So let's go ahead and look at this visually. So we have our chart here in the top left. We have a sample size of 30 for call center 1, sample size of 30 for call center 2. Then we have our sample standard deviations, which were given to us, of 1.2 and 1.5 respectively. Now everything below that, it's the same thing we had on the previous slide, so no new surprises there. But we have our margin of error of 0.7183. Remember, d bar will be the sample difference when we actually go ahead and calculate that. We'll do that in the next slide, I believe it is. So in the distribution, it will look like this. So we have our d bar there in the middle. That's going to be our mean difference. And then a 95% confidence interval, because our alpha is 0.05. So that means we have 2.5% in the lower tail and 2.5% in the upper tail. And of course in the middle, that's 95%. Now our t-critical values come from our t-table. We discussed that in the previous slides. So our t-critical on the lower end is negative 2.048, and our t-critical on the right-hand side is positive 2.048. And again, that just comes from the t-table. The values at the t-criticals is what our margin of error gives us over here on the left. The critical value in the lower and upper tail here is negative 0.7183 minutes for the difference, that's on the lower end, and 0.7183 minutes on the right tail critical. So this visually represents our margin of error that will go along with our difference. And again, you'll see how that all works here in a minute. But this is our 95% confidence interval for the difference given these two standard deviations in two sample sizes and our alpha level of 0.05. So let's say we go ahead and take our sample of 30 from each one, and the first call center gives us a sample mean of 11.91. And then of course the standard deviation was given to us of 1.20. We didn't calculate it or anything, it's just part of the problem. Our sample from call center 2, again, was size of 30, with a sample mean of 12.02, and that standard deviation was 1.50. Now everything else is the same. Degrees of freedom 28, alpha 0.05, and t-critical of plus or minus 2.048. So the only thing new here that we have are the means from each sample for each call center. A little bit of common sense here. Notice that the mean for call center 1 is 11.91. The mean for call center 2 is 12.02. Are those very close? Yes. So in your mind, you might want to be thinking sort of common sense that these two means probably are not different from each other. Now again, we're going to calculate it and know for sure, but I always urge the students I work with to use their common sense. With a sample size of 30, these two sample means are very, very close to each other. Now the difference here is the mean for call center 1 minus the mean for call center 2. So that's 11.91 minus 12.02. That gives us a difference of negative 0.11 minutes. So that is our d sub 1. That's going to be our difference, the difference between the sample means. So where d was in the margin of error formula, or our interval formula, that's where the difference will go. You can see it there in the blue. And everything else is the same. So we just go ahead and continue. Negative 0.11 minutes, that's our difference. And then the rest of this you've already seen. So we'll go ahead and do the math out. So our interval for the difference, based on these two samples, is negative 0.11 minutes plus or minus 0.7183 minutes. So again, based on this sample, that is our interval. So if we go ahead and do that math out, our interval estimate for the difference in these two call centers, as far as their time differences, is anywhere from negative 0.8283 minutes all the way up to 0.6083 minutes. And that is the 95% confidence interval for the difference between the call lengths, the average call lengths of these two call centers. That is a confidence interval for the difference, and the fact that it spans that interval will be very important, as we'll see here in a second. So everything we have here was in the previous slide. We have our table of information up here in the top left, then we have our interval down here in the lower left. So negative 0.11 minutes plus or minus 0.7183 minutes. That's our 95% confidence interval for the difference between these two means. So here's our distribution again. We saw this a couple of slides ago. So the interval for the difference from side to side of the confidence interval is 0.7183 minutes. Remember, that was our margin of error. So that is the dotted lines that extend down from the distribution. Now, if we measure this in actually standard errors, remember the standard error, which in this case, if you look over here on the left again, 0.3507 there in the red, that is our standard error. That's another way of saying that each standard deviation in our distribution of differences is 0.3507 minutes. So one standard deviation to the right is 0.3507 minutes. Therefore, two standard deviations would be 0.7014 minutes, and the same thing over to the left. Now remember, our T critical is 2.048. That's why the values there are 0.7183. But the standard error is just a standard deviation in the sampling distribution. That's why I went ahead and put those there. Now remember, our difference was negative 0.11 minutes. So that's not right there in the center. It's going to be about 1/3 of the way over to the left between 0 and -1 standard errors. Because remember, a standard error is 0.3507 minutes. Therefore, negative 0.11 minutes is about 1/3 of that over to the left. Now, the interval, the green arrows, that's the same width. No matter what the difference is, as long as the standard deviations are the same and the sample sizes are the same, the standard error remains the same. You can see it there in the red. As long as everything in the red is the same, the distance, and the alpha is the same, of course, the distance that these green arrows cover will always be the same. So our difference of negative 0.11 is there right where approximately where the brown arrow is in the distribution. And of course, the green arrows span the same width as the green arrows up there at the top. So that is our interval we calculated before. So the left end of the bottom green arrow is at approximately negative 0.8283 minutes. And then the end of the arrow on the bottom on the right is at approximately 0.6083 minutes. So that is our mean difference, and that is our margin of error, or our interval around that mean difference. So right there where the brown lines are. So what is our conclusion about this calculation? So based on our samples, the margin of error is plus or minus 0.7183 minutes. The 95% confidence interval estimate of the difference between the two call center population means is negative 0.11 minutes plus or minus 0.7183 minutes. So there's a 95% probability that this interval contains the true mean difference between the two call centers. Remember, that's how we interpret a confidence interval. There's a 95% probability that this interval up there above, negative 0.8283 minutes to 0.6083 minutes, there's 95% probability that that interval contains the true mean difference between the two call centers. Now, what we have to ask ourselves is 0 minutes, is 0 in this 95% interval? And the answer, of course, is yes. So if 0 is in that 95% interval, then we have to conclude that there is no evidence to suggest that there is a difference between the means of the two call centers. So we're always looking for that 0 point. If 0 minutes is in the interval, then we must conclude that there is no difference, based on the evidence we have, that there's a difference between the two call center means. So, wrapping a few things up. Mu1 is the mean of population 1, mu sub 2 is the mean of population 2. We're interested in the differences between the means, so mu1 minus mu sub 2. To conduct this analysis, we'll select two independent random samples, n sub 1 and n sub 2, from the two populations respectively. They do not have to be the same size, the samples, but ideally they are close in size. Otherwise, we have some problems with assuming variance and some variance differences and stuff like that. Now, when sigma is not given, so the population standard deviation is not given, we use S, the sample standard deviation, and therefore the t-distribution as a model of the sampling distribution of differences. And again, that goes back to stuff I'm sure you've already learned. When you use a sample, you use the t-distribution. We must also calculate the appropriate degrees of freedom, and we did that in the other formula. So from there, we proceed in finding the confidence interval for d bar, which is the mean difference, in the same manner as we would find the confidence interval for a single mean. So instead of a single population mean, we have a distribution of differences, or a mean of the differences. So the layout, again, is the same. So finding the interval, x bar plus or minus t sub alpha over 2 times the standard error, that's the single sample case. And then in the two independent sample case, looks basically the same in terms of its structure. D bar plus or minus t sub alpha over 2, because we're doing two-tailed, times, again, the standard error. Same basic structure. Okay, so that wraps up sort of our introductory example how to find the interval estimate of the mean difference. And I want to stress it's not all that different from what you did when you were estimating the mean and confidence interval for a single sample. You're using the exact same thing, except in this case it's the mean of the differences times the t sub alpha over 2, same thing you did before, times its standard error when we're actually using two populations. And of course, you have to calculate the degrees of freedom using that formula we did before. But basically, very similar. Even when you're looking at the distribution, the way it's laid out, the way the interval is laid out, instead of a single population mean, we have the d bar, which is the mean of the differences. But basically, everything else is the same. So stick around for the other videos in this playlist, and we'll talk more about and work more examples of the interval estimate and confidence intervals of the mean difference between two populations, including matched t-tests at the end of the playlist. So thank you very much for watching. I wish you the best of luck in your work and in your studies, and I look forward to seeing you again next time.